It is now my pleasure to introduce our first speaker of the day, Dr. Sang-Joon of Park Systems. He will be speaking on the recent advancement and prospect of scanning probe microscopy. His work over 20 years has built on diverse expertise in basic science and instrumentation and application development of SPM for nanometrology, especially for media and semiconductor industry and biomedical science. He has been recognized with various awards and nationally funded research grants. He is the Vice President and Director of Sales and Applications at Park Systems Corp. Currently, he is also serving as Chairman of ISO TC201 SC9 Scanning Probe Microscopy to facilitate the standardization of SPM technology. So please join me in welcoming Dr. Sang-Joon Cho.
So thanks for kind introduction. So today I will start with introducing our kind of development for last 3 years. And then, so this, I believe that scanning probe microscopy is not just one technology. Actually, this is kind of a broad and then wide kind of applications. I think that it can contribute every corner of the science technology. And then, you know, where the scale is different, something that we've never imagined happens. So when you see these golf balls, so when we see it like a 70,000 frame per second, so nobody will imagine this kind of things happen, you know. And then also when glass cracks, so it cracks instantly. But when you see this, you know, in very slow scales, you know, they spread these cracks, and then they spread in like a 200 microsecond, and then the speed of cracking goes to the 1458 meters per second. It means like a 4.2 mark. So it's faster than any airplane. So like this, so in here the scale key is the time, but same things happen when scale down and see the very small things. So that's why we are kind of making microscope. Going to the okay, so actually, so when we think about it, the science technology development of humankind actually start from the invention of a microscope. So when first we invented the microscope, optical microscope, people think about what will be the resolution limit of the optical microscope in 1839. And then people after people studied for 40 years, and in 1872, the honest app, and then they realized that this resolution is limited by the size of the light wavelengths. And also, same thing happens in electron microscope. So 1857, the cathode ray tube was invented, and people were studying how these electrons move in the magnetic field. And then the graduate student, Rosca, of the Professor Bush, and then he kind of refined Bush's work in predicting trajectory of electrons in this magnetic field. And then they built like a first electron microscope in 1931. And this is a 1933 model. And then after this, and then they received the Nobel Prize in 1986, together with the Gottwinnig and Heinrich Rohrer, who invented the first scanning probe microscope called scanning tunneling microscope. And then Ernest Rosca, the Professor Rosca, waited 50 years for Nobel Prize, and then he kind of passed away like 1.5 years later. But anyway, among the scanning probe microscope, actually the most contributed or the widely affected the scanning probe microscope is the atomic force microscope. Actually, AFM. This AFM was invented in Stanford University in 1985, and first the paper I think it comes in 1986. So due to timing, they couldn't receive the Nobel Prize, but instead they received the Cavalli Prize in 2016. And when the AFM was invented, the Park Systems CEO, Dr. Sang-Il Park, was a graduate student. So after graduation, he started the company commercializing the atomic force microscopy for the first time. So since then, Park System is concentrating developing AFM, and now we have some result. So like last 3 years, we are picking up really fast, and now we think that we are the probably maybe next year we will safely say that we are the market share #1 in atomic force microscopy. But when you say so, we think that we realize the power of atomic force microscope or scanning probe microscope and potential of it, you understand, but like it start very slow. Well, why is it? Because it's too difficult for use it for the everybody the new novice. It's really hard to control this AFM because there's too much parameters. So, but when you think about it, the same thing happens in the photography. So when first invented this photography, the only expert can operate this this instrument to take a picture. But in 1988, Kodak ran this advertisement, like you press the button and then we do the rest. So that start this camera industry, pick up, and then now everybody can take a picture. So we are trying to do the same thing in atomic force microscope. This is the most advanced research grade the automated AFM. So auto probe exchange, the auto probe detection. So recognize all the what kind of a probe is, so what this probe has been used. So record the a history of the cantilever, and then auto laser alignment, and so on. So all these automatic options make it easier for people to use. And then, but not just easy of use, also we realized the superior performance on the seeing the real high resolution. And a few months ago, we see this DNA origami. So each nucleotide is about 3.5 nanometer. It's the wide, and then also each nucleotide has about 3-4 nanometer each tide, and then you can actually really decode those things. So it was amazing. We also see this kind of pictures using FX40. So now we go to the application of atomic force microscope in semiconductor industry. AFM has wide application, not just semiconductor industry, but this time, so right now, AFM has most impact in this industry. So today I will focus in introducing AFM in the semiconductor field. So now semiconductor industry is really important because in the market or the society require like a big data analysis or a system simulation, artificial intelligence, and that those kind of requests. So makes this device make it smaller and smaller, and then also complex 3D structures like FinFET and so on. So in order to measure these kind of devices, like conventional metrological inspection cannot work anymore. So they're looking for the new solution. So that's why the AFM is one of the candidate for solving those problems. So in order to go into the industry market, so we had to develop not just the AFM technology, but also like automations, and then also the process requirement for the AFM. And when you think about it, when electron microscope was first invented, so it takes about 55 years to go into the real industrial application, but AFM, it only takes like 30 years. And when you think about it, this is the front end of the line process of the semiconductor process. And then in here, AFM providing valuable data of critical dimensions and profile profiles, and then inspection and review, and then CMP dishing and erosion data. But in this front end of the line, the metrology, we couldn't provide the thickness in AFM. It's out of its technology. But like 2 months ago, actually, Park Systems, we acquired Accurian in German metrological company who are developing imaging spectroscopy ellipsometer. This is specialized for measuring thickness. So since this is an Asia Korea conference, I like to announce proudly that it's an amazing thing. It's a historical thing because Korea, we still import more than 90% of metrological tools, advanced metrological tools. And Germany is really the top country, or really the advanced country for metrological technology. But in a Korean metrological company, this is the first time in history to acquire German metrological company. But we are not just doing that for the purpose of the growing the company. Actually, we really think that if we make a synergy between these technologies, we can really contribute, and then we can really provide a solution to our industrial partners and others. That's our objectives. Okay, it's not go to the okay, and then so when we think about it, currently the function of AFM, the used in semiconductor field is a really basic one. It's just this part, but the AFM technology can do much more, like electrical property measurement, mechanical property measurement, or chemical property, or magnetic, or all sort of things. So I believe that this is the time that the AFM technology in the status of complete. Actually, it's just the beginning. So it has much more potential to provide the solutions, not just the semiconductor industry, but to many other industries. So among the semiconductor industry, let's go to see the defect. Actually, defect used to be when we make the big patterns, and then we can ignore the defect of a size of a tenth of a nanometer defect, but because it doesn't obstruct the process severely. But when pattern becomes smaller and smaller, like a tenth of nanometer, and these 30, 50 nanometer defect make a severe impact on process engineering. So now the controlling defect is important. And then also when defect comes, not just seeing where it is, we need to understand what kind of a defect it is and what's the characterization of it. So that way we can understand how it happens and how we can remove it, or how we prevent those defects on the wafer. So, and especially the EUV, so last several years, EUV technology has been spoken widely. So in EUV, they making patterns so small, and then in order to make this EUV beam, they are using plasma to vaporize the thin material, and that thin material, that way, these thin particles scale up on the wafer. So this controlling defect is really important. And let's go to see how we can control. So first, we need to find the defect. So we align from the receiving coordination from other optical inspection tool, and then we align, and then we try to we find the defect on the wafer using AFM, and then we review those defects and provide the data of height, area, volume, roughness. But the weakness of AFM technology is throughput. It's a scanning method, so it's not photographic method. So that even inevitably, it's throughput-wise is weaker. So there's 3 ways to overcome the throughput. So it's just doing really fast scan or using multi-probes, but those approaches has not been successful so far. So we think that let's rely on other technology who can contribute to these problems. So we think that white light interferometry, because it provides the same data format of a 3-dimensional thing in large area. And then, so in large area, we can quickly see those surfaces three-dimensionally using WLI. And then when we have an interested area, we can zoom in to see with the atomic force microscopy. And now we are developing application of it. So let's see the quickly of this animation of how we combine WLI and AFM. So this object, when there's a different materials in WLI images, has a kind of eventually have errors because it's a light reflect differences. And now we go to the AFM to these surfaces, a little bit slow, but it can, compensate the errors by the WLI. So that way we can have more faith in WLI data. And then not just the correcting WLI data, like in wide area, we're looking at it with the WLI, and we quickly find the problem places, the hotspot detection, and goes in to review with the AFM. And when first scanning tunneling microscope was in Nobel lecture, so Goh Bining and Heinrich Roth, original idea then was not to build a microscope, but rather to perform spectroscopy locally on an area less than 100 angstrom in diameter. But for about 20 years, it is STM and SPM technology only used for mostly they used for topography. And now we develop kind of a smart method of a pinpoint mode for the most quantitative nanomechanical characterization. The reason is most popular to the research people, because we can control contact force, like a dwell time, approach retract speed, and retract distance, all can be programmed to optimize the measurement. And then so like this, you just zoom in, and then this is topography. And then this is topography by pinpoint. And so when you, I don't know if you can see the difference in the screen. There's a little bit different because in here it's a non-contact, but in here like a pinpoint is poking the pixel by pixel. But we can get adhesion, modulus, stiffness, and quantitatively. And then those, we also contribute not just nanomechanical property measurement using pinpoint. We also correctly measure the electrical property of the sample. So we can get this short circuit current and open circuit voltage, and we can smartly kind of get the data of efficiency of the solar cell materials. That way they kind of publish the very good paper in the society. And now I will introduce another exciting technology called the photonic force microscope. So for a long time, so people called AFM or STM is a blind microscope because, so when you are using light microscope, you see the colors. Color means it's the chemical kind of information, but AFM is a kind of looking through the tip, and you can get also the physical or electrical properties, but not chemical properties. So people think that you call the blind microscope, but there's another solution. So I will not explain kind of deeply, but if I explain quickly, so it's a metal coated tip, and then there's the IR quantum cascade laser. So this IR spectra, so IR laser is easily observed by the materials, and then when they do, and then they make different molecular vibration, depends on the different molecules. And then those molecular vibration makes different attractive force. And then AFM tip is so sensitive, they can kind of detect what kind of the attraction force is changing here. So, and then we found out this signal is really well aligned with the Fourier transform, the IR spectroscopy, the FTIR. So when we see this compared with the other technology, so when we see that transmission electron microscope, So it has a really really good elemental information detections. And with a 200 nanometer, like a 0.2 nanometer resolution. But even with the same element, so depends on the structure. So it becomes whole different molecules. That's why we need molecular detection. So one of the good candidate for molecular detection is a TOF SIMS, and then it has about 200 nanometer resolution, but it's not easy to use. So most widely used technology is FTIR, but the problem is that the scale is 10 micrometer. So people looking for another method for another solution, another technology for the chemical identification. One is the Raman technology, but the problem of Raman technology is the Raman signal is too weak, and then also a lot of other the operational difficulties. But the PIFM has we can do the molecular analysis in nanoscale, and then so both IR absorption, the spectra, as well as we can map the chemical in the surface in less than 5 nanometer range. So most kind of when we see the technical difference between other thing and then PIFM is most of this is Raman and FTIR. They're kind of detecting the signals using photo detectors, but it really limit the lateral resolution because it's a kind of how can I say, the signal is diffuse, but the PIFM, the detector is a probe itself. So probe is the detector, so it depends, resolution depends on the fine radius of the probe. So we can easily go to the 5 nanometer and less than 5 nanometer resolution of a chemical identification. So this is the PIFM and FTIR data of a nylon, PS, polyimide, and then PMMA. You can see it really correlate very well. And then the reason it correlates very well is that so in FTIR, these materials are really homogeneous. If they have some other materials, and then this FTIR signal become really, how can I, noisier, Okay, and let's go to see the silicon germanium and silicon oxide FinFET structure. This is silicon germanium and silicon oxide. And then one of the benefit of a PIFM is we can go through all the wavelengths to see what kind of the material in one spot. And then when we know the structural wave number, and then we designate the wave number, in this case, the 1120 for silicon oxide, and only the silicon oxide is light up. So we know that the light area is the silicon oxide. And when we run with the wave number of the 1022 for silicon germanium, and we know that this area has the silicon germanium. And this is comparison of the torus images, which taking the same FinFET of silicon germanium, silicon oxide, and you can see which technique is better. So like when we go through so when we see the defect, so we can identify those chemical identification of the defect. And then we first think that this must be the silicon carbide defect, and also went through the 790 wave number for silicon carbide, it shows up. But later on, with a different wave number, we found out so only half of the particles showing up. So in fact, it is not just a silicon carbide. It's combined with something else. So this way we can kind of inspect and kind of try to understand what happens in the surface. And this is another example. So it's a biologically or environmentally friendly material called the polylactic acid. Kind of we're trying to replace the plastics, so it can decomposable. But the problem is mechanical the structure of a polylactic acid is too weak, especially like hot water, and then they melt away. So in order to strengthen the mechanical properties, we make a kind of composite with alkylate copolymer. But after the mixing these the materials, we like to know how they combine, how they structure. So using PIFM with 1750 for the PLA, and then PLA, and then it shows like a dot around here, and then 1721, and then it light up for the alkyl copolymer, and then we can see a copolymer is exist as like this. So this way we can understand the materials, the chemical structure of the materials. And lastly, there's another interesting application of SPM. So I told you that in EUV process, defect control is so important. So people try to use mask defect refuse. So usually they use a wet process to remove the defect, but when defect becomes like a 30 nanometer, 50 nanometer, it sticks to the surface so hard. So the wet process cannot remove those defects. So that's why the AFM is utilized to go through this process to remove the defect. So like there's two type of defect, like a hard defect, like a hard chrome, and then we scratch it to make a pattern again. And then if there's particles on the pathway of the light, and then we push these particles to some place where the light path doesn't disturb. So like let's see the video of it quickly. Yeah, so this is a mask. So when we UV going continued, and then those particles are like a build up, and then so this mask is a little bit different from wafer. So we locate we position this mask, and yeah, this is very important. So kind of more important thing than removing particle is not damaging the mask by using the tip. So when there is the defect, this is hard defect, we designed and then run, and then we kind of go through it. When we apply this technology, most important thing is like a pre-step control. So we require perfect control of the cantilevers. Yeah. So let's go. So we started from the LCD kind of metrology and chip makers and wafer the manufacturers. Now the AFM market expanded to the OLED or micro LED or mask manufacturers or packaging or substrate like PCB manufacturers. So I think that AFM market will continue to kind of expand. And we also developed softwares. Due to times, I'm not going into details. If you go to our website, you can see these new software features. And also when you go out, okay, when we go out, there's FX40, actually you can see the automatic operation of FX40 by yourself. It's just outside right now. So I will just skip this, the animation. So in conclusion, I truly believe AFM technology is a state-of-the-art measurement technology, but that has just entered the period of growth from the embryonic state. So there is much more potential, and there is a lot to learn. So please, so if you come to our website, there's many information. So when you go through it, if you have questions, please feel free to contact us. Then we will try to help you as much as I can. And for the acknowledgement, and this year, last year, we received the largest, the nationally funded study, the nationally funded project. So one is for the semiconductor technology related, the SPM development, and also the kind of UV mask defect detection analysis technology, and infrared or WRI microscope, combined with the FPM project, and also kind of multi-channel extreme scanning probe convergence technology development. So I think the next 3-4 years, you will see the exciting development of SPM, and then so let's see what will happen. Thank you very much. So if you have any questions, so okay, maybe due to time, so we will go to the next speaker.
Hello.
Okay, so go to the next speaker then. Yeah.
Thank you very much for that wonderful talk, Dr. Cho. So do you have any questions for Dr. Cho? So we do have one questions online, Dr. Cho. So how do you measure OCV and efficiency indicator in your page 27?
It's a electrical measurement, and then so there's a mathematical kind of a definition to measure this electricity. So it's kind of due to time constraint. It's not easy to explain all at this time. So I will kind of answer your questions independently, but it's not that difficult.
Thank you, Dr. Cho.